We have already introduced several thermodynamic potentials that can be summarized here. A thermodynamic system with a specified set of state variables has a given internal energy U and entropy S. If we focus on ideal gases, the variables describing the state of the system are the pressure P, the volume V and the absolute temperature T of the gas. A thermodynamic process transforms the state of the system from one state to another one while the system may exchange energy with its surrounding in the form of the heat Q and the work W. Thermodynamic potentials also describe the state of such a system, and their change can characterize the nature of the processes transforming the state of the system. This table shows the 5 thermodynamic potentials already defined in the lecture. In the first 2 rows we can see the internal energy U and the entropy S of a system. The enthalpy H of a thermodynamic system is defined by the sum of its internal energy U and the product of the pressure P and the volume V. The Helmholtz free energy or simply the free energy F of a thermodynamic system is defined by the difference between its internal energy U and the product of its temperature T and entropy S. The free enthalpy or the Gibbs potential G of a thermodynamic system is defined by the difference between its enthalpy H and the product of its temperature T and entropy S, which is equal to the internal energy U, plus the pressure P times the volume V, minus the temperature T times the entropy S. The relationships between the different thermodynamic potentials are illustrated in this figure. Here we represent the potentials and the products P times V and T times V by different bars arranged in 4 lines. If we compare the first line with the second one, then we obtain the definition of the enthalpy H, while its comparison with the third line gives the enthalpy in terms of free energy and entropy. Similarly, in the second and third lines we can see the decomposition of the internal energy U into the bound energy T times S and the free energy F. The first and the last lines also show that the enthalpy H is the sum of the bound energy T times S and the free enthalpy G. By comparing each line with another one, we can express any of the thermodynamic potentials in terms of the rest of the potentials. As the name of the thermodynamic potentials indicates, these 5 quantities are state functions. In the state space with the state variables x1, x2, ellipsis, xn of a thermodynamic system, the state of the system can be represented by a point P in the state space. Then each potential are evaluated at the point P, that is any thermodynamic potential phi I is a unique function of the state variables x1, x2, ellipsis, xn, where phi I denotes the internal energy U, the entropy S, the enthalpy H, the free energy F and the free enthalpy G. As already mentioned, the state variables of an ideal gas are always the pressure P, the volume V, and the temperature T of the gas. In a more general treatment of thermodynamic systems, the amount of the working substance is not fixed, and its mass, the amount of species or the number of gas particles also becomes a state variable. Here we use the number of particles Ni to describe the amount of the substance in the thermodynamic system. The index I denotes the different species in a multi-component systems with more than one type of species. The variables xk represent the state variables associated with external forces acting on the system, such as gravitational or electromagnetic forces. Since each thermodynamic potential phi I is a state function, its change between any point P0 and the point P in the state space only depends on the initial and final states of the system, and is independent of the path calligraphic P of the process between these two states. In other words, the differential of any potential phi I is an exact differential, and it can be expressed as the sum of the partial derivative of the potential with respect to each state variable, times the differential of the corresponding state variable. When we introduced the 5 thermodynamic potentials, we also studied the extremum principle stating that these potentials change during a thermodynamic processes in an isolated system such that they reach extrema at equilibrium. Since this principle follows from the first and second laws of thermodynamics, we will apply them to present the quantitative analysis of thermodynamic equilibrium. The first law of thermodynamics states that the infinitesimal change in the internal energy U of a system is equal to the sum of the infinitesimal amount of heat Q absorbed by the system, and the infinitesimal work W done on the system during the process. By applying the second law, we can see that the sum in the right-hand side is less than or equal to the temperature T of the system times the differential of its entropy S, plus the infinitesimal work given by minus the pressure P of the system times the differential of its volume V. Here we assume that only the pressure volume work is done in the process and no external forces act on the system. Then we obtain our first inequality stating that the differential of the internal energy U is less than or equal to the temperature T times the differential of the entropy S, minus the pressure P times the volume V. We can also write this inequality in the form where the differential of the entropy S is greater than or equal to 1 over the temperature T times the differential of the internal energy U, plus the pressure P over the temperature T times the differential of the volume V. These two inequalities are therefore equivalent. Now we can use the definition of the enthalpy H to write its differential as the differential of the sum of the internal energy U and the product of the pressure P and the volume V. By factoring out the terms in the parentheses and substituting the first inequality into the differential of the internal energy U, we can write that dH is less than or equal to the temperature T times the differential of the entropy S minus the pressure P times the differential of the volume V, plus the differential of the product of the pressure P and volume V given by V times dP plus P times dV. Then we obtain T times ds plus V times dP. As a result, our third inequality tells us that the differential of the enthalpy H is less than or equal to the temperature T times the differential of the entropy S, plus the volume V times the differential of the pressure P. We also derive the differential of the free energy F in the same way. By applying its definition, we can write dF as the differential of the difference between the internal energy U and the product of the temperature T and the entropy S. If we factor out the terms in the parentheses and substitute the first inequality into the differential of the internal energy U, then we obtain an inequality stating that dF is less than or equal to T times ds minus P times dV, minus the differential of the product of T and S given by the sum of S times dt and T times ds. Since the right-hand side can be reduced to minus S times dt minus P times dV, our fourth inequality states that the differential of the free energy F is less than or equal to minus the entropy S times the differential of the temperature T, minus the pressure P times the differential of the volume V. Similarly, the fifth inequality for the differential of the free enthalpy G can be obtained from the differential of the difference between the enthalpy H and the product of the temperature T and the entropy S. By factoring out the terms in the parentheses and substituting the third inequality into the differential of the enthalpy H, we can write that dG is less than or equal to T times ds plus V times dP, minus the differential of T times S given by the sum of S times dt and T times ds. Then we obtain minus S times dt plus V times dP, and the final inequality states that the differential of the free enthalpy G is less than or equal to minus the entropy S times the differential of the temperature T, plus the volume V times the differential of the pressure P. In these inequalities the differentials of the five thermodynamic potentials appear in the left-hand side, whereas some linear combinations of the differentials of the potentials and the state variables can be seen in the right-hand side. The potentials and variables appearing in the differentials are called the natural variables of the potential in the left-hand side of the inequalities. In this table, we display the pair of the natural variables for each thermodynamic potential. The natural variables of the internal energy U are the entropy S and the volume V, as seen in the first inequality. The second inequality shows that the natural variables of the entropy S are the internal energy U and the volume V. The natural variables of the enthalpy H are the entropy S and the pressure P, as seen in the third inequality. This table shows that one of the natural variables of internal energy, entropy and enthalpy is a thermodynamic potential, and the other one is a state variable. It is not the case for free energy and free enthalpy where the natural variables are only state variables. For the free energy F the natural variable pair is the temperature T and the volume V, and the natural variables of the free enthalpy G are the temperature T and the pressure P, as seen in the last two inequalities. The extremum principles related to the thermodynamic potential stating that each potential has an extremum in thermodynamic equilibrium, are derived from the laws of thermodynamics. Then these extrema can simply be determined from the inequalities based on the same laws if the natural variables of the potentials are held constant, that is when their differentials are equal to zero. Then the right-hand side of the inequalities vanish and we conclude the following. In an isentropic and isochoric process, the infinitesimal change in the internal energy U of a system is less than or equal to zero. The internal energy of the system decreases during the process, and it has a minimum when the system reaches equilibrium. In an isochoric process, where the internal energy of the system is also constant, the infinitesimal change in the entropy S of the system is greater than or equal to zero. The entropy of the system increases during the process, and it has a maximum when the system reaches equilibrium. In an isentropic and isobaric process, the infinitesimal change in the enthalpy H of a system is less than or equal to zero. The enthalpy of the system decreases during the process, and it has a minimum when the system reaches equilibrium. In an isothermal and isochoric process, the infinitesimal change in the free energy F of a system is less than or equal to zero. The free energy of the system decreases during the process, and it has a minimum when the system reaches equilibrium. In an isothermal and isobaric process, the infinitesimal change in the free enthalpy G of a system is less than or equal to zero. The free enthalpy of the system decreases during the process, and it has a minimum when the system reaches equilibrium. We already presented these extremum principles for each potential, and we have only shown now that they directly follow from the set of inequalities derived here. The extremum principles of course hold for general thermodynamic processes as well, and they simultaneously hold for each potential in a given process. We illustrate this fact by plotting the functional relation between the internal energy U, the entropy S and the volume V of a thermodynamic system. This functional relation is represented by a surface in the three-dimensional subspace of the state space, where the surface is restricted to only one quadrant in the coordinate system for the sake of simplicity. We can illustrate an isentropic process by cutting this surface with a plane of constant entropy, where the intersection of the surface and the plane defines a curve along which the internal energy changes. At the point P, the internal energy has a minimum and it represents an equilibrium point of the system. If we cut the surface with the plane of constant internal energy such that their intersection passes through the point P, we can see another curve along which the entropy changes and it has a maximum at the equilibrium point P. This shows that the system has minimum internal energy and maximum entropy in its thermodynamic equilibrium. In a general thermodynamic process with the equilibrium point P, the curve representing the change both in the internal energy and the entropy of the system passes through the point P, such that the internal energy decreases and the entropy increases simultaneously along the curve. Similar plots can also be created for including all the thermodynamic potentials as illustrations of the extremum principles. In order to derive the fundamental equations or relations of thermodynamics, we only need the 5 inequalities describing the infinitesimal change in the thermodynamic potentials during quasi-static processes. If these processes are reversible, then the inequalities become equalities, whereas the strict inequalities hold for irreversible processes. In other words, these inequalities are evaluated along a path of the process in the state space of a system, where the right-hand sides of the inequalities depend on this path. However, thermodynamic potentials are state functions, and their infinitesimal changes in the left-hand sides of the inequalities are exact differentials. As a result, they depend only on the initial and final states of the system in the infinitesimal process. These differentials measuring the infinitesimal change in the potentials between two states give the extrema of the right-hand side of the inequalities, as the irreversible path of a process connecting the two states approaches a reversible path. As a result, when the inequalities become equalities in the reversible limit, we can interpret them as the equations evaluated in the initial and final states of an infinitesimal process. The general description of infinitesimal changes in the thermodynamic potentials includes the change due to chemical reactions or the work done on the system by external forces. Here we only consider the contribution of chemical reactions because the change in the numbers of particles Ni in a multi-component system depends on these reactions. In order to describe chemical reactions in a thermodynamic system, we define the chemical potential μI associated with the species I in the system by the partial derivative of the potential phi j with respect to the number of particles Ni for the species I at a fixed set of potentials and state variables under a given condition. In other words, chemical potential measures the change in any thermodynamic potential under given conditions per the number of particles. Here the given condition represents a set of potentials and state variables determined by the potential phi j are held constant during the change in the number of particles. By taking chemical reactions into account, we can generalize the 5 equations that are known as the fundamental equations or relations in thermodynamics. The first one states that the differential of the internal energy U is equal to the temperature T times the differential of the enthalpy S, minus the pressure P times the differential of the volume V, plus the sum of the chemical potential μI times the differential of the number of particles Ni with the index I running over all the species in the system. If we solve this equation for the differential of the entropy S, then we obtain 1 over the temperature T times the differential of the internal energy U, plus the pressure P over the temperature T times the differential of the volume V, minus 1 over the temperature T times the sum of the chemical potential μI times the differential of the number of particles Ni. The third relation tells us that the differential of the enthalpy H is given by the temperature T times the differential of the enthalpy S, plus the volume V times the differential of the pressure P, plus the sum of the chemical potential μI times the differential of the number of particles Ni. The next relation is for the free energy F and states that its differential is equal minus the enthalpy S times the differential of the temperature T, minus the pressure P times the differential of the volume V, plus the sum of the chemical potential μI times the differential of the number of particles Ni. Finally, the differential of the free enthalpy G is given by minus the enthalpy S times the differential of the temperature T, plus the volume V times the differential of the pressure P, plus the sum of the chemical potential μI times the differential of the number of particles Ni. As already seen, the first 2 equations are equivalent and we have 4 independent fundamental relations describing infinitesimal changes in the 5 thermodynamic potentials. This figure shows the relationships between the different terms in the fundamental equations excluding the terms with chemical potentials. We represent the terms in the relations by different bars arranged in 4 lines. The first fundamental relation can be constructed from the left-hand side of the second and third lines, indicating that T times ds is equal to the sum of du and P times dV. Similarly, the first 2 lines in the figure shows that dH is given by the sum of T times ds and V times dP. We can construct all of the fundamental relations for the thermodynamic potentials from this figure by adding the sum with the chemical potential to the result. Obviously, the second fundamental equation, where the factor of this sum is -1 over T, follows from the first relation with the positive sum. By introducing the contribution of chemical reactions to the change in thermodynamic potentials, we have increased the natural pairs of the potentials to 3. Here we can see the thermodynamic potentials as functions of their natural variables. For the internal energy U, the natural variables are the entropy S, the volume V, and the number of particles Ni. In the case of the entropy S, this functional relation is inverted, and the natural variables are the internal energy U, the volume V, and the number of particles Ni. For the enthalpy H, these variables are the entropy S, the pressure P, and the number of particles Ni. Finally, the natural triplet for the free energy F is the temperature T, the volume V, and the number of particles Ni, whereas this triplet consists of the temperature T, the pressure P, and the number of particles Ni for the free enthalpy G. These natural triplets have a crucial role when we express a given thermodynamic potential as a function of another potential and the state variables. We can apply the fundamental equations of thermodynamics to give a quantitative analysis of the conditions for thermodynamic equilibrium. Let us consider a thermodynamic system separated into 2 subsystems with a wall. We assume that the system is isolated from its surroundings with a boundary which is an adiabatic, fixed and impermeable wall preventing the exchange of any heat, momentum for pressure work, and matter. We also assume that no external forces act on the system. These conditions have the mathematical expression stating that the differential of the heat Q transferred across the boundary wall, the pressure work W done on the system, and the mass m of the substance flowing across the wall vanish. As a result, we have 2 subsystems isolated from their surroundings by the boundary wall that can interact with each other depending on the properties of the separation wall. The state variables and functions describing the states of the interacting subsystems are labeled with the numbers 1 and 2. Then we can write that the total internal energy U of the system given by the sum of the internal energies U1 and U2 of the individual subsystems is constant. Similarly, the total volume V of the system given by the sum of the volumes V1 and V2 of the subsystems is constant, and the total number of the particles N in the system given by the sum of the number of particles N1 and N2 in the corresponding subsystems is also constant. In such a setup, the total entropy S of the system is equal to the sum of the entropies S1 and S2 of the individual subsystems written as functions of the internal energies, volumes, and numbers of particles of the subsystems. In order to examine the conditions of thermodynamic equilibrium in the whole system for different types of the separation wall, we will apply the second fundamental equation expressing the differential of the entropy S as 1 over the temperature T times the differential of the internal energy U, plus the pressure P over the temperature T times the differential of the volume V, minus 1 over the temperature T times the sum of the chemical potential μI times the differential of the number of particles Ni. This equation can be used to determine the change in the entropies S1 and S2 of the subsystems during any process leading to equilibrium. First, we discuss the condition for thermal equilibrium where the average heat flux vanishes in the whole system. We assume that the initial temperatures T1 and T2 of the subsystems are different, and there is a net heat flux between the subsystems during their thermalization. Such a condition can be examined if the wall separating its 2 subsystems from each other is diathermal, fixed, and impermeable. A diathermal wall allows heat flux between the 2 subsystems, and any infinitesimal change in the internal energy U1 of the first subsystem is equal to minus the infinitesimal change in the internal energy U2 of the second subsystem as the total internal energy of the system is conversed. Since the wall is fixed and impermeable, the differentials of volumes V1 and V2, and the numbers of particles N1 and N2 vanish. If we suppose that the temperature T1 is greater than the temperature T2, then the net heat flows from the warmer subsystem to the colder one. That is, the change in the internal energy U1 of the warmer subsystem is negative, whereas the change in the internal energy U2 of the colder one is positive. During the thermalization of the system, its entropy S increases and reaches its maximum at equilibrium. Then the condition for thermodynamic equilibrium is that the differential of the entropy S of the isolated system vanishes. Since the total entropy is the sum of the entropies of the subsystems, ds is equal to the sum of the differentials of the entropies S1 and S2. By applying the fundamental relation for each subsystem and taking into account that the differentials of their volumes V1 and V2, and their numbers of particles N1 and N2 vanish, we can write that the sum is equal to 1 over the temperature T1 of the first subsystem times the differential of its internal energy U1, plus 1 over the temperature T2 of the second subsystem times the differential of its internal energy U2. We can eliminate one of the differentials from the right-hand side because the differential of U1 is equal to minus the differential of U2. As a result, ds is equal to the difference between 1 over T1 and 1 over T2, times du1. In thermodynamic equilibrium, the differential of the entropy S vanishes for arbitrary values for du1, and the terms in the parenthesis must be 0. Then the temperatures T1 and T2 are equal, showing the thermodynamic equilibrium at the end of the thermalization of the system is a thermal equilibrium. Now we conclude that the condition for thermal equilibrium in the whole system is that its two subsystems must have the same temperature. Although we established this criterion when we introduced the concept of heat in thermodynamics, here we formally derived it from the fundamental equation and the extremum principle for entropy. We can also illustrate how the extremum principle determines the direction of the thermalization taking place in the system. The principle tells us that the entropy S increases during the process, and its differential must be positive. Since we suppose that the temperature T1 is greater than the temperature T2, it follows from the last line in the equation chain of the vanishing differential of entropy that the infinitesimal change of the internal energy U1 of the warmer system is negative, as we have already shown it. Conversely, if the temperature T1 is less than the temperature T2, then the equation for thermal equilibrium shows that the differential of the internal energy U1 must be positive, that is, the net heat must flow from the warmer second subsystem to the colder first one, increasing the internal energy of the colder subsystem. Now we examine the condition of another type of equilibrium in the system called mechanical equilibrium. In this case, we assume that the wall separating the two subsystems from each other is diathermal, movable and impermeable. Then the heat flow is still allowed between the two subsystems, and the differential of the internal energy U1 is equal to minus the differential of the internal energy U2. Since the movable wall allows the change in the volumes V1 and V2 of the subsystems, we can state that the differential of the volume V1 is equal to minus the differential of the volume V2. For the impermeable wall, the differentials of the numbers of particles N1 and N2 vanish. If the system reaches thermodynamic equilibrium, then the differential of its entropy S, that is the sum of the differentials of the entropies S1 and S2 of the subsystems, vanishes. By applying the fundamental equation, we can write this sum as 1 over the temperature T1 times the differential of the internal energy U1, plus the pressure P1 over the temperature T1 times the differential of the volume V1, plus 1 over the temperature T2 times the differential of the internal energy U2, plus the pressure P2 over the temperature T2 times the differential of the volume V2. Since du1 is equal to minus du2 and dv1 is equal to minus dv2, we can express ds as the difference between 1 over T1 and 1 over T2 times du1, plus the difference between P1 over T1 and P2 over T2 times dv1. As the expression must vanish for arbitrary and independent values of du1 and dv1, the terms in both parentheses must individually vanish, that is 1 over T1 minus 1 over T2 is equal to 0, and P1 over T1 minus P2 over T2 is equal to 0. Then we conclude that the temperature T1 is equal to the temperature T2, and the pressure P1 is equal to the pressure P2. The equality of the temperatures, that is the thermal equilibrium in the system, is just the consequence of the diathermal property of the wall separating the two subsystems from each other. The equality of the pressures in the two subsystems is the result of motion of the wall balancing the pressure forces acting from both the sides of the wall. If the pressure is initially different in the two subsystems, then the net pressure force acting on the wall moves it, such that the pressure will be equalized in the whole system as the result of the changing volumes of the subsystems. Since the pressure produces mechanical forces exerted on the wall, the balance of forces involves that the system is in mechanical equilibrium. Now we examine the condition for a third type of equilibrium in the system called chemical equilibrium. Such a condition can be examined if the wall separating the two subsystems from each other is diathermal, fixed and permeable. For a diathermal wall, any infinitesimal change in the internal energy U1 is equal to minus the infinitesimal change in the internal energy U2 due to the heat flow across the wall. Since the wall is fixed, the differentials of volumes V1 and V2 vanish. For a permeable wall allowing the exchange of the matter between the two subsystems within the isolated system, we can write that the differential of the number of particles N1 is equal to minus the differential of the number of particles N2. We can start again with the vanishing differential of the entropy S of the system as the general criterion of its thermodynamic equilibrium, which is equal to the sum of the differentials of the entropies S1 and S2 of the subsystems. By applying the fundamental equation, we can write this sum as 1 over the temperature T1 times the differential of the internal energy U1, minus the chemical potential mu1 over the temperature T1 times the differential of the number of the particles N1, plus 1 over the temperature T2 times the differential of the internal energy U2, minus the chemical potential mu2 over the temperature T2 times the differential of the number of particles N2. Since du1 is equal to minus du2 and dN1 is equal to minus dN2, we can express ds as the difference between 1 over T1 and 1 over T2 times du1, minus the difference between mu1 over T1 and mu2 over T2 times dN1. As the expression must vanish for arbitrary and independent values of du1 and dN1, the terms in both parentheses must individually vanish, that is 1 over T1 minus 1 over T2 is equal to 0, and mu1 over T1 minus mu2 over T2 is equal to 0. Then we conclude that the temperature T1 is equal to the temperature T2, and the chemical potential mu1 is equal to the chemical potential mu2. Since the wall of separation is diathermal and the heat flux across the wall can thermalize the two subsystems, we have obtained the criterion of thermal equilibrium again. At the same time, the wall is also permeable, allowing matter flow between the two subsystems. The second criterion tells us if the chemical potential is different in the two subsystems, then this difference produces a generalized force for matter flow. As a result, some amount of matter is exchanged between the two subsystems till their chemical potentials become equal and the system reaches chemical equilibrium.